we have to get gotta get a test in this week. So the test is gonna be Friday. Review is gonna be Thursday. Wednesday, I will not be here. We have UIL competition, and so I will have a sub, and I will be gone all day at UIL competition. So Wednesday is going to be like a makeup day. I'm going to open up a bunch of the assignments, maybe not all of them, but some of them. If you want something open, just let me know, and you can work to kind of get caught up on Wednesday. Today and tomorrow, we're going to do the ideal gas law. And so we're going on to the next one. The combined gas law is still open. There's a bunch of people that didn't really finish it, and more people than I would like that didn't even start it. And so that is open through Wednesday. If you'd like to bring that up. From this point on everything we did the first 3 weeks, if you do something on it, obviously they're all closed except for the combined gas law. But if you want me to open it up and you add to it or bring your grade up or finish some questions, you need to send me an email so I know to go in and change your grade. Because I got a lot of students, I got a lot of people making stuff up. And if you don't tell me to change your grade, I won't know to do it, and it'll just stay as the old grade. And so grades have already been submitted for progress reports. I will probably print those up today and give them to you tomorrow. Excuse me. And so we're going to go ahead and get started on the ideal gas law. And you can kind of see from this, the ideal gas law, we're going to shift gears a little bit. We're still going to have a formula. You're still going to have to solve for X. But notice, what's the difference between this formula and every other formula that we've done in this section?
There's an R.
There's an R. That's one of the differences. And the other difference is there's no ones and twos. So in these types of problems, nothing is changing. You have one specific gas at one time and place, and it's going to have one pressure, one volume, one moles, and one temperature. You just got to figure out one of those numbers. They're going to give you 3 of them, and you have to figure out the 4th one. And then the new thing that we're introducing is R, and we'll talk about R. R is a constant. The bad news is R is a little bit tricky, but the good news is it's not that bad, and you look it up every single time. So sampling will give you the information you need to figure out what R is, and then it's just another number that you plug in, and you don't have to worry about it from there. So let's take a look at the PowerPoint. Let's do some example problems, and then we can get going on the actual assignment. So let me grab my pointy stick. My laser pointer died, so I'm back to the old ages with the yardstick. Let's see. So the ideal gas law. Here's the idea behind the ideal gas law. The ideal gas is a hypothetical gas. So they're just imagining this gas. I mean, there are real gases that are ideal, but it obeys the kinetic molecular theory perfectly. And so it is doing things that we can predict. If it's obeying the kinetic molecular theory, I can go into the formulas that I use in kinetic molecular theory, and I can tell you all sorts of stuff about it. That's the ideal part. It does what we think it does. It follows the formulas. I can use the formulas to tell you stuff about this gas. Experiments on gases under near ideal conditions show that pressure times volume divided by the number of moles and temperature is equal to a constant. And I mentioned that constant. What's the letter for the constant?
R.
R. That's the new thing that we're introducing. And so they kind of show you, let me draw it over here. Turn the lights on. If we come over here and we take the ideal gas law formula, and it's P times V equals N times R times T. PV equals nRT. It rhymes. It's easy to say. Let me just label it ideal gas law. Put a big square around it. Now, if I wanted to get R by itself, what would I have to do? Divide the N and T over the other side. So that's what they're kind of saying there. R, that constant, is equal to the pressure times the volume over the moles times the temperature. And so R is actually something we can calculate if we know all the other stuff. If not, we kind of have to do a little bit of looking up, a little bit of research. But If you're missing one of these, you have to have the R in order to solve this equation. And so you're never really going to use the equation like this. They're just kind of explaining to you how they got to the point where we understand what R is, and we got these numbers for R. And basically with most constants, some constants make sense. Sometimes you have to learn a lot about the subject to understand the constants. But the best way, I think, to describe a constant for like high school level is basically we understood the relationship between the pressure and the volume and the moles and the temperature. But when we were doing the math, it never came out right. So we would make the formula, we'd do the math, and then we go into the lab and work with the gas and see if it fits the formula. And it was always just a little bit off. By a certain amount, it's always off and it's wrong. And they're trying to figure out why. And they're like, I don't know why. And turns out there's an extra number that they need, an extra bit of mathematics that has to go in there in order for all your numbers to come out correctly. And the good news is, especially with this kind of math, experimental math, I can actually go into the lab and see if it works correctly. It's not abstract. It's actually a physical thing. It's a gas in a container that I can go check. And so they were able to work this out and figure out what that missing number was. And they called that R, which is called the gas constant. So it's known as the ideal gas constant. It's denoted by R. And the value of an ideal gas constant depends on the units of pressure. And that's the thing. We have a standard unit for volume. It's liters. We don't use gallons. We don't use, I guess, what else would you use besides gallons or liters? Ounces or anything like that. We use liters. For temperature, we use Kelvin. We know that because if you get Celsius, you have to convert to Celsius. And moles is just moles. There's no other way to talk about moles. But pressure, we had different pressures. We talked about atmospheres as a pressure, kilopascals as a pressure, and millimeters mercury as a pressure. And so even if you're not super familiar with all three of those, you know that there's different ways to measure pressure. We don't even use the most common one for us, which is pounds per square inch, what we measure the tire pressure in our cars. So there's lots of different ways to measure pressure, which means if I have a number that is based on the pressure, for every different unit I use for pressure, I'm going to have a different number. And the truth is, we only use 3 in this class. If you were to look up R as a gas constant, there's a whole long list of R's that you might have to look up at any given point in time. So we're not going to use that whole long list and make this even more complicated. We're just going to use these 3. And I'm going to write them on the board real quick. But the idea here is, before you build your problem, you're going to go in and look. You're going to hunt down your pressure and find out what your pressure is. Is it in atmospheres? Is it in kilopascals, kPa? Or is it in millimeters mercury? Once I know what of those 3 my pressure's in, now I know what my R value is going to be. So R gas constant, come down here, and if it's in ATMs, ATM, your gas constant is 0.0821, 0.0821. If your pressure is in kilopascals, kPa, your R value is 8.31. And if your pressure is in millimeters mercury, mmHg, your kPa is 62.4. So you can see, this one's like way below 1, way less than 1. This one is 8.3, and this one's 62.4. If you multiply or divide by the wrong one of these, your answer is going to be way off. If you choose the right one, that will lead you to the right answer. So you have to make sure that you choose the right one of these to plug in every single problem. So when we're doing ideal gas law, you want to go to the problem, find out what my pressure is, and then come up here on the board, or Sapling will have it for you. These are also listed on that study sheet that I gave you way when we started these gas laws. So if you still have that, you can have that. Or just write this down in your notes. A bunch of you have been working your problems in like a spiral, run some scratch paper. Just jot these down in your notes, and you always have them there with you. Also, of course, this video will be online, and they'll be written on the board. So That's what we have with R. You've got to find your pressure. What pressure do they give you? That tells you what number to use. You just plug it in like it was a number that Sapling gave you, and you just go ahead with your problem that you want. So, the ideal gas law. Let me turn the lights off. Ideal gas law is the gas law that describes the relationship between the pressure, volume, and number of moles and temperature of an ideal gas. And the key here is, again, like I said, we're not changing anything. There's no 1, there's no 2, there's no before or after. It's just one gas at one point in time that doesn't get changed. That's what we're worried about. So your formula is the classic PV equals nRT. P is pressure, V is volume, N is moles, R is that new gas constant that we have, and temperature is T. Remember, your temperature has to be in Kelvin. They will try to mix you up by giving it to you in Celsius. So here's our example problem. What is the pressure in kilopascals? So they're asking me for the pressure. So right away, I told you to figure out your R, you hunt out what your pressure is. Well, in this problem, I don't know what the pressure is, but they know that I need this to actually work the problem. So they tell me my pressure is going to be in kilopascals. So now I can go and find my R value. If I'm in kilopascals, what should my R value be on the board over there? 8.31. So 8.31 is what I'm going to use for my R value here. That's what I'm looking for. Then they keep going and tell me I have 2.51 moles. I have a temperature of 308 K, which I don't have to convert because I'm already in Kelvin. And then a volume of 7.08 liters. I'm ready to go. I just need to plug everything in and solve for the pressure. So I'm going to come over here and work this on the board quickly. And what we have, PV equals nRT. I don't know the P, so I'm going to leave that there or just put an X in there for it. My volume is 7.08 liters. I
thought that was a decimal and then a 7.
Oh no, yeah. It's a times. I could use a little X. I use the little dots for the times. Is everybody okay with that? Yeah, you can use parentheses. You can use a little X, or if you're like full on math, you just don't put anything there. You put two numbers behind, right next to each other with nothing in between. You know you got to multiply them. But yeah, just P times 7.08 is my volume. Then I go to the other side of the equal sign and I get my moles, my R value, and my temperature. My moles are 2.51 times my R value, which I already figured out because I'm in kilopascals, has to be 8.31. And then times my temperature, which is already in Kelvin, so it's 308. And now, how do I get the P by itself? Divide by the 7.08. So I'm just going to divide this over to the other side. And when I do that, these two cancel out. And what I'm left with is my problem, which is multiply the top three numbers, divide by the bottom one, bing, bang, boom, done. Is everybody good with that? So if we do this just to get an answer and see if we did it right for Sapling here, I got 2.51 times 8.31 times 308 divided by 7.08. And I have 907.38 kilopascals. Where did I put my marker? P equals, what was it, 907.38? Yeah. 907.38 kilopascals. So if we go forward here, where did I put my pen now? There it is. If we move forward a little bit, we see that they did the same thing that we did. They got to the same problem and the same answer, 907 kilopascals. Let's see if they give us another example here. Yes. So one more example. How many moles? This time they're looking for N, moles, of argon gas are contained in a sample at 311 K temperature with a volume of 855 milliliters. Now, here's the thing. When we look at our volume or our Pascal units, our R units, notice, come back here. Oh, come on. If you can see in the units down here, what are all my volumes at? And my units next to my R values?
Liters.
They're all in liters. So we got to convert that to liters before we can use it. We could use milliliters, but the R value number would be different and you'd have to go and look it up. And so just to use these three, we got to make sure that our volume's in liters and our temperature is in Kelvin. So that's what we need to use this. So when we go forward, we're going to have to convert the milliliters to liters. Next problem, sorry. There we are. And then we have a pressure of 836 millimeters mercury. So what's the R value for millimeters mercury? 62.4. So I look at what my pressure unit is, and that tells me what my R value will be. So let's go ahead and plug these numbers in, and we'll see what we have. Let me erase this. Again, we've got PV equals nRT. My pressure is the millimeters mercury. It's the 836 millimeters mercury. So I have 836 times. My volume is 855 milliliters. What do I do to that to convert it to liters? Does anybody remember? Move it 3 times to the left. So this is going to be 0.855 liters. So to convert from milliliters to liters, you move it 3 times to the left, and you get 0.855 liters is equal to N. I don't know what the N is. That's what they're asking me for, my moles. I do know my R value. What's my R value for this problem? The 62.4 because of my pressure. My pressure is in millimeters mercury, so it's got to be 62.4. And then my temperature they give to me is 311. So now I got to get the N by itself. How do I move these numbers to the other side? I divide by them. So I'm going to divide by 62.4 times 311 on both sides. When I do that, these cancel out, and I'm left with my problem. Multiply the top 2 numbers, get that answer. Multiply the bottom 2 numbers, get that answer. And then get your final answer by dividing top over bottom. And what I get is 836 times 0.855 divided by 62.4 times 311. Did I do that right? Yeah, I guess I did. And I got 0.0368. N equals 0.0368. So that's a small number, but that's not too bad because moles, we can have really small numbers of moles because it's a huge amount of atoms. So that's not anything I think we should be concerned about. We'll see if we actually got it right or not. Let's see. So they get everything here. They're going to ask, do we need any conversions? And the answer is yes, we have to convert our volume into liters if we're going to use these R values. So we did that. And then we plug everything in, and we get 0.0368, which is exactly what they were looking for. So I believe that will be the last, another example. Let's just see what it is. What's the temperature of 0.064 moles of nitrogen gas with a volume of 0.34 liters and a pressure of 0.56 atmospheres? I'm not going to do this on the board. We're just going to go through it quickly. They're asking me for temperature, and my pressure is in atmospheres. So what's the R value I need to use for atmospheres now? 0.0821. So that's what I'm going to do there. So they plug everything in. We have our moles. We have our volume, which is already in liters, so we're good. We have our pressure, and then we have our R value, which is the 0.0821. We're looking for temperature. They plug everything in, and they're going to divide the numbers that are next to temperature away over to the other side. This is the math they get, and their temperature comes out to be 373, which seems like a good temperature in Kelvin. So I think that's the last problem. Yes, I will leave this problem up. You can go ahead and start on the assignment. It's assigned. I don't even know how many questions are on it. Let's see.
13.
13. See, that's not too bad. That's not too bad. So you should be able to get a decent way through this today, I believe. But take your time on it. If you have any questions, let me know. If you get it wrong once or twice and don't know how to get to the correct answer, come up here and I'll take a look at it. What you got? Yes, go ahead. Make it quick. To do what?
Oh my gosh, that's the
Let's see. So like, it's gonna be my salary for like the next 30 years. So it's gonna be like in the hundreds of thousands for sure. Maybe over 30 years, you might be even like over $1 million. I don't know.
Could he be banking?
No installment plans. I need cash up front. Yeah.
I'll give you about like $2 grand.
No. Not worth it. Not worth it.
I would
Because I do a student's assignment and I'm gonna get fired and then I got no money. So yeah. No, it would snowball real quick.
really.
Yeah, it would. All right. Yeah, I think that's it. So if you have any questions, let me know. Know that the combined gas law is still up, but I would suggest doing this right now today because we just went over it. And so it'd be nice and fresh in your mind and be able to get some problems done. So if you have any questions for anybody at home, just email me. Let me know. Have a nice day.